sections. So we're going to do section 5 today. Section 5 is called the alternate series. So that's another topic in series. About a few things in the first sections. We talk about the sequence in section 1. We talk about the series, introduction to series in section 2. We talk about the integral test and the P series. In section 3, we talk about a comparison test. In section 4, we can use those methods or strategies to determine whether a series converges or not, and that's the key part of a series. All right, convergence or divergence. So today we're going to talk about another kind of series that we will see a lot. It's alternate series because the terms in the series alternate in sign, such as negative half to the n. So if n is 0, you get the negative half to the 0's power, which is 1, so that's positive. And then n equal to 1, the next term will be negative 1 half to the 1's power. So that's negative half, so it's negative. And then next you get negative half to the square when n equal to 2. So you get 1/4, which is positive again. And then next term will be negative. So it's like positive, negative, positive, negative. And some of the other series maybe start from negative. So you got negative, positive, and so on. So in any case, the terms in the series alternate in signs. So 14 just gives a condition for the convergence of this kind of series. Negative 1 to the n if we just separate the magnitude of the terms of each term, and then you get a sign of negative 1 to the n. So an will be positive in this case. You can rewrite this series in this format. Or negative 1 to the n plus 1 times an, and then the only difference between this and the negative 1 to the n is just you change the sign. Okay, so you just change n to n plus 1. For the exponent, that means you change the sign from positive to negative and from negative to positive for each term. Okay, but again, this is just the typical alternate series in general form. So when is this kind of series converge? There are two conditions. The first condition, limit of an must be 0. Okay, the magnitude of the terms in the series has to converge to 0. It must have a limit of 0, and this is required for every series if it converges. Okay, so this first condition is general for any series to converge, and the second condition is specific for alternate series, and it does not apply for any other series. And the condition 2 is a of n plus 1 is less than an. So that means the magnitude of the alternate series have to decrease. And the first condition, says that it has to converge to 0. So if we combine these two conditions, it basically says the terms of the alternate series must have magnitude decrease and converge to 0. All right. Okay, so we can use this criterion to determine the convergence or divergence of alternate series. For example, if we're talking about the series of negative 1 to the n plus 1, I'm sorry, I missed the 1 here, times 1 over n. This is the alternate series because we got negative 1 to the n as the sign, and the 1 over n is a magnitude. So we just need to check the two conditions, whether they're met or not. So in this case, the magnitude magnitude of this series for each term is an equal to 1 over n. And obviously the limit of 1 over n is 0 as n approaches infinity. Also, the magnitude decreases as n increases. If you write n plus 1, it will be 1 over n plus 1 if you replace n by n plus 1. And that is less than 1 over n. Obviously, you get the larger denominator, the whole fraction is less, becomes smaller. So so that's less than 1 over n, which is a, and so two conditions are met. So that means this series converges. Okay, the alternate series. All right, let's do another example. This time we got a series of n over negative 2 to the n minus 1. Okay, so this is again an alternate series because you get negative to the n minus 1 as the sign. And again, this just change from positive to negative and negative positive, back and forth. So this terms altered in sign. So it's alternate series, and we need to see, whether this series converges or not. Again, just two conditions, and the first condition is general for all the series to converge, as I said before. So you want to find the limit of a and make sure it approaches 0 as n approaches infinity. So an in this case is the magnitude of the series. What you do is just take out the negative sign, the sign term in the series. So it's just n over 2 to the minus 1. Okay, if you take out the negative 1 in here, the sign to the negative 1, negative 1 to the minus 1 actually. And to find the limit of this an as n approaches infinity, we can use L'Hopital's rule, but we need to first define a function f of x based on this the series or sequence. Just change n to x everywhere in the formula for an. So we get x over 2 to the x minus 1. That's always the way to do it. And then you just take the limit of the function as x approaches infinity, and that should be the same as the limit of the sequence a and as n approaches infinity. All right. And so we got x over 2 to the x minus 1 as x approaches infinity, both the numerator and the denominator blows up. You got a 2 to the x minus 1. When x is large, then you multiply 2 by itself many times. So the number gets bigger and bigger and blows up. So this is an indeterminate form that we can use L'Hopital's rule to find the limit. So what we do, just take a derivative of the top and the bottom. And then we get a 1 on the top and the 2 to the x minus 1 times 0 and 2 at the bottom. And then you can see as x approaches infinity, the bottom, it still has the term of 2 to the x minus 1 that blows up. And then you get a constant of n and 2. On the top, you can just get 1. So obviously, the denominator blows up as x approaches infinity. So the whole thing just has a limit of 0 in here. So the first condition for convergence of the alternate series satisfies. And then you need to show or check whether the magnitude of an decreases as n increases. That's the second condition. So we need to find an plus 1 and compare it with an. So again, it just replace n by n plus 1 everywhere in an. So we get an n plus 1 over 2 to the n plus 1 minus 1, which is which we can write as 2 to the 2 to the n. Okay, and then we can split up as 2 to the n minus 1 times 2 to the 1, or just 2, right? If you add n minus 1 with 1, you get n. Okay. And there's a reason we want to do that. We want to compare this term with the previous term, an. And so you can rewrite the top, the numerator as n times n plus 1 over n. And then if we do that, we can separate n over 2 to the n minus 1. And then we are left with n plus 1 over n over 2. Okay, so the first part of n over 2 to the n minus 1 is just the an. So we got this an to compare with an plus 1. And then n plus 1 over n over 2 is just n plus 1 over 2, and if we do it. Now this will be, reading as n plus 1 over n plus n, and you get the an to multiply the whole thing. So n plus 1 over n plus n obviously is less than or equal to 1 because n is greater than or equal to 1 in this series, remember? So that means the whole thing is less than or equal to an. So the second condition is satisfied. So this we use the different techniques, tricks a little bit, and they are pretty used pretty extensively. Those kind of small tricks when you compare different numbers. So two conditions are made. So by the theorem 14, the alternate series converges. All right. Any questions? Okay. So let's do another one. This time we have alternate series of -1 to the n plus 1 times n plus 1 over n. Again, this is alternate series. So you have to check that first. It has to be an alternate series. It has to be like a plus or minus, plus or minus. So the magnitude here, an, is just n plus 1 over n if you take off the sign of -1 to the n plus 1. Well, obviously, if you take the limit of an as n approaches infinity, you're not going to get 0, okay? And so n plus 1 over n you can break up into over n and 1 plus 1 over n using the numerator, and then n over n is just 1, and then the limit of 1 over n is just 0 as n approaches infinity. So at the end, you get the limit of n equal to 1. So the first condition even is not satisfied. So the alternate series diverges. Okay. So that's this example, and let's do another one. Okay, this time we got a series of 2 over 1 minus 1 over 1 plus 2 over 2 minus 1 over 2 plus 2 over 3 minus 1 over 3 plus 2 over 4 minus 1 over 4. So, the denominator of this series just increased by 1 for every 2 terms. And the numerator of the series just change back between 2 and 1. And this is also an alternate series, as you can see, plus minus, plus minus, plus minus, and so on. So the first term, A1 is 201. That's the magnitude, which is 2, and the magnitude of the second term is 1 over 1, which is 2 if you ignore the sign. The third term is 2 over 2, the magnitude. The magnitude of the fourth term is 1/2. Okay, again, you don't consider the sign here. And the fifth term is 2/3, the magnitude. So you can see initially we do have the magnitude decreases, but as it goes to A4 to A5, you can see it's increasing now. 1/2 is less than 2/3. So the condition of an plus 1 less than an is not satisfied. So the series diverges. Okay, we got another divergent alternate series. And actually, if you rewrite this series back, group in two terms each time, you get 2 over 1 minus 1 over 1 plus 2 over 2 minus 1 and a half plus 2/3 minus 1/3 plus 2/4 minus 1/4. Okay, then you're going to get the 2 minus 1 as the first term, and 2 minus 2 minus 1/2, which is 1/2. 2/3 minus 1/3 is just 1/3. 2/4 minus 1/4 is 1/4, and so on. So, and this comes back to the harmonic series we discussed in section 3, and we already knew it was divergent. So we can use the alternate series to show that the series also diverges. All right. So you can do the same problem in different ways. Any questions? Okay. So that's this example. Okay, the next thing is called the alternate series remainder. Okay, we're trying to find the sum of alternate series. In case this series converges, then we want to find a precise number for this sum. Okay, for the series, but sometimes it's not even possible to do that. And then we can have some good estimation of the sum of the series by truncating a small tail from this series. So in this theorem 15, it talks about the error when we truncate the series, the tail of the series, how much error we get if we do that. So we have suppose we have a convergent alternate series, and obviously the second condition an plus 1 less than an is satisfied. And then let's just take the sum of the first n terms of this alternate series, okay? And use that to approximate the whole series of the infinite terms, the sum of infinite many terms. And then we define the remainder of the series as s minus Sn. Okay, so that's the precise value of the series minus the first n terms sum. We call that the remainder. Okay, and then we can conclude from the theory that theorem. That's what it says in the theorem says this error. Okay, so we're trying to approximate s by Sn. So if you subtract the s and the Sn, you get error for the approximation, right? And the theorem just says that the error by doing this kind of approximation or truncating will be less than or equal to an plus 1. Then magnitude of the next term of the series from truncating. Okay, so let's see what it means by this theorem and how we use it to estimate the sum of alternate series, convergent alternate series. So we have a series in this example for -1 to the n plus 1 times 1 over n factorial. So this is the alternate series. You get a sign term. Again, it should be -1 instead of negative. And then n factorial, as I said, it's just the product of the numbers from 1, 2, 3, 4, 5 up to n. So let's just use the first 6 terms of the series to approximate the whole series of the infinitely sum of infinite many terms. Okay, so according to the theorem, if we use S6, the sum of the first 6 terms to approximate the sum of the infinite many terms, then the arrow, so that's the absolute value of S minus S6, will be less than or equal to A7. The next term, the magnitude of the next term in this series. So, all right. So we get this inequality. And then we can write this inequality as a compounded inequality. You know, each absolute value inequality turns out to be a compounded inequality, and it will be negative A7 less than or equal to S minus S6 and less than or equal to A7, or S minus S6, the arrow for the truncation will be between negative A7 and positive A7, in other words. Okay, so if you add S6 to each part of this compounded inequality, you're going to get S is between S6 minus A7 and S6 plus A7. Okay, so let's try to, calculate S6, and then we can also compute A7 and plug in those numbers into this inequality and see what we get. So S sub 6 is just this first 6 terms of this series. Okay, again, we should have a -1 here instead of negative. So the first 6 terms will be 1 over 1 factorial when n equals 1, -1 to the 1 plus 1, which is -1 square is 1. So the first term is positive. And then when n equal to 2, you get 2 plus 1 as 3. So -1 to 3 is negative. So you get the -1 over 2 factorial. And the third term, 3 plus 1 is 4. -1 to the fourth is positive. So you get 1 over 3 factorial. And the next term will be -1 over 4. And then you get the other terms of 1 over 5th positive minus 1 over 6 factorial. Okay, both. So this is the first 6 terms. You should know how to write down the terms of a series. The first few terms of series or sequence. Okay, so we can compute those numbers a little bit. 1 factorial is 1. 2 factorial is 2 times 1, so that's 2. 3 factorial is 3 times 2 times 1, so that would be 6. And 4 factorial is 4 times 3 times 2 times 1, and that's 24. And 5 factorial is 5 times 4 times 3 times 2 times 1, and that's 120. And then 6 factorial, do it the same way, you get the 720. So you just add those fractions and then approximate it or convert it into decimal. You get this number 0.63194 approximately. Okay, and then you can also do a 7, which is 1 over 7 factorial magnitude of the 7th term in this series, and it's just 1 over 5040, and that's about the 0.00002. So plugging those two numbers in the compounded inequality we got, which is S6 minus A7 less than equal to S, less than equal to S6 plus A7. So plugging those two numbers, we get a 0.63194 minus 0.0002 less than equal to S, less than equal to 0.63194 plus 0.0002. Okay, so then you just do this decimals a little bit. You get 0.63174 on the left and 0.63214 on the right. So S will be between those two numbers. So S, remember, is the sum of the infinite series, is the precise value of this infinite sum. We cannot get the accurate value, precise value for this S, but we can have a pretty good estimation of this sum. It will be between 0.63174 and 0.63214. Okay, so that's pretty good estimation or approximation. So we at least we know what the value of A uh, is and you know how accurate that estimation is. All right. Any questions? Okay, let's go to the next topic. Um, okay, we're going to introduce two new concepts in here. It's called absolute and conditional convergence. First, let's just start from a theorem. It says if the series of absolute AN converges, so you get a series, any series, some of the terms may be positive, some may be negative. They're not necessarily alternate series. Okay, so this is series in general, any series in general. So if the series of the absolute value of AN converges, then the series of AN itself has to converge. Okay, because you got AN dominated by absolute of AN. Okay, so then we have two situations here. The first situation is if the series of absolute value of AN converges, then obviously the series AN itself converges from theorem, and then we call this series AN absolute convergence. It means the series of the absolute value of AN converges, and then both the series of absolute value and the AN itself converge. Okay, so absolute convergence is a strong statement, but in some cases you may get the AN converge, but the series of the absolute value of AN does not converge. Okay. And because this series and converges, conditional convergence. Okay, it's still AN still converges, but the absolute value of AN does not converge the sum. So this is called the series AN conditional convergence. All right. So let's just try to do some examples. The first example says having to determine convergence, divergence. Oh, why did I write twice? Or even three times? Oh, okay. Oh, yeah. Divergence, absolute convergence, conditional convergence of the series. Okay, so it's no problem. Of this series, -1 to the n factorial over 2 to the n. Okay, so again, this is the alternate series. We can check the two conditions, and the first condition says the limit of AN has to be 0. And let's just check the magnitude of AN, which is n factorial over 2 to the n. If you take out the -1 to the n, the sign term. Again, n factorial is n times n minus 1 times n times 2 times all the numbers down to 3, 2, and 1. And 2 to the n is just the 2 of n copies of 2 multiplied by each other. By, And then you have n numbers from 1 to n on the top multiplied together. So then you can basically split this quotient into n fractions multiplying each other. So you can group n with 2, you get n over 2, and n minus 1 over 2, n minus 2 over 2, and so on. And then you get 3 over 2, 2 over 2, 1 over 2. Okay? Well, obviously, this will be greater than or equal to 1/2 because all the numbers you multiply will be greater than or equal to 1 for n greater than or equal to 2. Okay. So that means this AN will be greater than or equal to half. So the limit of AN will never be 0. So then the series diverges. Okay. So it's an alternate series, and the first condition is not met. So the series diverges. All right, let's just do another example. This time we got another alternate series -1 to the n over square root of n. Again, this is alternate series. You just check the two conditions. So first find the limit of an. Obviously, 1 over square root of n as n approaches infinity. You get square root of n approaches infinity. So the limit is indeed 0. The first condition is met. Also, n plus 1 is 1 over square root of n plus 1, and that is less than 1 over square root of n because you get the denominator a little bigger in the first place. So that's 1 over square root of n, which is a n, and then you get n plus 1 less than a n. So the second condition is also met. So this series, the alternative series, does converge. But then if you take out the negative sign or the alternate sign, -1 to the n, you just get 1 over square root of n for the series, and that's just 1 over n to the half. And this is a p series with p equal to half, and that's diverges. So remember, the p series diverges and p is less than or equal to 1. Okay. So, so the magnitude or the absolute value of the an or the terms, the series of the absolute value of the terms diverges, but the series itself is alternate series and they converge. So this series we call it conditional convergence. Conditional convergence. All right. So let's do another example. This time we got another series -1 to the n times n plus 1 over 2 to the 3 over 3 to the m. So we got a very complicated expression, but it really doesn't matter. If you consider -1 to the n times n plus 1 over 2, it just gives you a sign, okay? It's just a -1 to some number, so it's either positive or negative. So that's just a sign. And indeed, it's not alternate series. You cannot use the criterion for alternate series. But if you just consider the absolute value, it's just 1 over 3 to the n, okay? And the top is just a sign. So we know this is 1 over 3 to the n, which is the 1/3 to the n, and that's a geometric series with the ratio r equal to 1/3, which is less than 1, and that converges. So so that means the series of the absolute value of the terms converges, and that guarantees this original series with the sign converges. Remember, in the theorem says absolute value series converges, and the original series also converges. So this series, original series with the sign, is called absolute convergence. All right. Okay. Let's do one more example. This time we also get alternate series -1 to the n over ln of n plus 1. So this alternate series, again, we come back to the alternate series, and the magnitude is just 1 over n. So obviously the limit of an or limit of 1 over n of n plus 1 is 0 as n approaches infinity. That's no problem. You know, and then the natural function just blows up as n approaches infinity, and so you get the denominator blows up, so the limit is 0. But then we need to check the second condition. If the an plus 1 is less than or equal to n, and this is also true. An plus 1 is just 1 over n plus 1 plus 1. So it is just n plus 2. And then that's less than 1 over n plus which is a n. So the magnitude of the series does decrease. So the two conditions for alternate series conversion satisfies. So this alternate series converges itself. And then let's look at the series of the absolute value of the terms. So we get the 1 over n of n plus 1 if we take out the signs of each term. Okay, so that's just 1 over n2 plus 1 over n3 plus 1 over n4 and so on. Okay, this is n start from 1, you get n plus 1. So the first term is 1 over n2. Okay. So, and that's greater than 1/2 plus 1/3 plus 1/4 plus, so on. Because 2 is greater than n2, 3 is greater than n3, 4 is greater than n4, and so on. So if you flip it, then you got the inequality reversed. And you can easily see from the graph, what graph, you got the 9y equal to x, and then the natural log function y equal to n and x. You can see the line of y and x, y equal to x is on the top of n and x, the curve. So that means the x is greater than n and x. Okay. So, and then you can easily find that this sum 1/2 plus 1/3 plus 1/4 is just the harmonic series without the 1. So if you include that term 1, that becomes the harmonic series. So it's this sum is -1 plus the harmonic series. All right, and then the harmonic series diverges. So obviously, we got the series of the absolute value of the diverges. Okay, you get u plus -1. It doesn't matter because the other product of 1 over n sum up to infinity. So the whole thing -1 is still infinity. So this series of the absolute value of the terms diverge. So, but the series itself, the alternate series itself, converges. So this is again an example of a conditional